The construction of the Apollonian Gasket was known already to the ancient Greeks, and it is attributed to Apollonius of Perga. Interestingly, the radii of all the touching circles are rational numbers, and even better, the figure can be scaled such that all the inverse radii have integer values. They are shown in the animation. The outer circle has an inverse radius of -2, where the negative sign indicates that the other circles are touching from the inside. The Apollonian gasket, traced out by the spider, is one that belongs to an infinite family of gaskets that all share these properties and that are explored in this video. We start our construction with two parallel lines. Between the lines, a chain of circles is inserted. The diameter of the circles equals the distance of the lines and the distance between neighboring circles, so they will touch each other and the parallel lines by construction. Next, the gaps are filled with smaller circles. Have a look at the connection between the x-coordinate of the center and the radius of the circle. Can you recognize a pattern? Marvelously, for any position x that is a fully reduced fraction, you can place a circle. When its radius is twice the square of the denominator of this fraction, the circle perfectly fills the gap between its neighbors. This is only the beginning of the story. Circles can also be found for gaps above the x-axis. The pattern that we've just found can be generalized. To do so, let's label some circles with their inverse radius. The straight line along the x-axis can be thought of as a circle with infinite radius. The inverse radii of four mutually touching circles fulfill a nice property. For instance, take the four circles labeled with 0, 2, 2, and 8. For these numbers, one finds that the square of their sum is twice as large as the sum of their individual squares. This turns out to be valid for any four mutually touching circles and is known as Descartes' theorem. It can be used to calculate the radius of a circle that fills the gap inside the ring of three other circles. Let's take the gap between the three largest proper circles in the animation. One has to solve the following equation. The appropriate solution is 1/24. With this information, the circle is readily constructed. The radius for the circle of the next larger gap to the left follows from the equation. It solves to 1/56. Of course, computer algebra quickly repeats this procedure for a large number of circles. The Mathematica script first solves Descartes' equation and then computes the center of the circle in spirit along the lines of the shown construction. The data for the radii and the centers are imported into GeoGebra. As always, you can find these scripts in the video description. The ribbon of circles can now be turned into the Apollonian gasket by a circular inversion. The mirror circle is highlighted in red. When all the circles are reflected, the spider's web materializes. However, when you think back, the spider didn't draw any circle at all. Instead, it connected all the touching points of the circles and joined them by its thread. This will be the second approach to this Apollonian gasket. It will show up as a limiting process of the repeated application of two complex transformations. Stay tuned if you are interested for more.